There is a lot of AI research coming out every day. As a person who spends a lot of time on arXiv, which is where most scientific research is shared, I can tell you that there are hundreds of AI research papers being published every day. Last month, a new paper was released, and it caught the attention of most people and was a topic of discussion among the scientific community for the whole month. It was the introduction of a new paradigm shift when it came to machine learning. Deep learning has been the go-to method of doing recent machine learning, but what if we had a better architecture than multi-layer perceptrons? This is where KNS come in. Kolmogorov-Arnold Networks is a new machine learning architecture that aims at replacing multi-layer perceptrons as the go-to architecture to develop machine learning models. It was released on May 2nd, and it gained a lot of attention immediately because of the promising results it showed compared to multi-layer perceptrons. In this video, I will try to go over the most important details of the paper without getting too technical. So what are KNS and how do they compare with multi-layer perceptrons? According to the research paper, Kolmogorov-Arnold networks are inspired by the Kolmogorov-Arnold representation theorem. While MLPs have fixed activation functions on nodes, neurons, KNs have learnable activation functions on edges, weights. KNs have no linear weights. Every weight parameter is replaced by a univariate function parametrized as a spline. I know most of you will ask, what is the Kolmogorov-Arnold representation theorem? Well, it was introduced by the two guys in the name. Vladimir Arnold and Andrei Kolmogorov established that if f is a multivariate continuous function on a bounded domain, then f can be written as a finite composition of continuous functions of a single variable and the binary operation of addition. In a sense, they showed that the only true multivariate function is addition, since every other function can be written using univariate functions and sum. The paper claims that this seemingly simple change makes KNs outperform MLPs in terms of accuracy and interpretability. For accuracy, much smaller KNs can achieve comparable or better accuracy than much larger MLPs in data fitting and PDE solving. Theoretically and empirically, KNs possess faster neural scaling laws than MLPs. For interpretability, KNs can be intuitively visualized and can easily interact with human users. Whereas MLPs are inspired by the universal approximation theorem, KNs are inspired by the Kolmogorov-Arnold representation theorem. Like MLPs, KNs have fully connected structures. However, while MLPs place fixed activation functions on nodes, neurons, KNs place learnable activation functions on edges, weights. As a result, KNs have no linear weight matrices at all. Instead, each weight parameter is replaced by a learnable 1D function parametrized as a spline. KNs nodes simply sum incoming signals without applying any nonlinearities. One might worry that KNs are hopelessly expensive since each MLP's weight parameter becomes KN's spline function. Fortunately, KNs usually allow much smaller computation graphs than MLPs. So what advantages do KNs possess that MLPs lack? The first is accuracy. KNs have been shown to be more accurate than multi-layer perceptrons and require fewer parameters as well. They can achieve lower training and validation loss compared to fully connected layers. In addition to being accurate and needing fewer parameters, which are learnable activation functions, they can work in continual learning without catastrophic forgetting, which plagues multi-layer perceptrons. The second advantage is that they can generalize better than multi-layer perceptrons. Not only do they perform well with the training and validation loss, but they also outperform MLPs on test loss and accuracy. Another advantage that KNs promise over multi-layer perceptrons is that they are easily scalable. A new concept that KNs highlights is a distinction between external versus internal degrees of freedom, parameters. KNs benefit from the fact that they have both external degrees of freedom and internal degrees of freedom. External degrees of freedom, that MLPs also have but splines do not, are responsible for learning compositional structures of multiple variables. Internal degrees of freedom, that splines also have but MLPs do not, are responsible for learning univariate functions. The final advantage that KNs have, and in my view the most significant one, is interpretability. Since KNs have learnable activation functions rather than linear weights, means that the black box problem is resolved. This means that we can interact with KNs, making them interpretable and easy to learn. They, however, do not lack a few limitations. The most notable one was their inability to work with sequential data. This means that they are extremely costly to train compared to fully connected layers. However, with the hype they have received, more research is being done and hopefully the problem of working with sequential data will be resolved. Such papers show how AI research is progressing, and just like the transformer changed the game, another new architecture will be introduced and keep pushing the boundaries of what AI can achieve. New architectures do not mean they come to replace existing ones, but can complement them. A good example of where KANs can be useful is in scientific research. They would work better than transformers. In other use cases, we may need more than one architecture. I would like to hear your thoughts on this one. Consider leaving a comment below or liking the video.